Recording in progress. Okay, please go ahead.
Okay, sure. Thank you very much, Professor Redcar, for providing me this opportunity to share my research here. And yes, because I'm a new faculty here, I'm currently actively looking for PhD students. So if you're interested, just reach out to me. You can find my email address, and we can have a talk together. Yeah. And today I'm going to talk a little bit about my research. Let me see. Okay, here. Okay,
It dropped.
yeah.
So it dropped. Just a second. I know it will be tricky if you're not used to Zoom.
Okay.
So okay. So this is what they see now.
Okay.
Go ahead.
Yeah. Okay, you can see the screen, right? Okay, cool. So the topic of my talk today is advanced data modeling and diagnostic for intelligent manufacturing systems. And so here's a content. So first I give an overview of my research, and then I introduce a focus topic, and then I talk about two other research topics, and finally I give a summary and talk about my expectation to the student, etc. So in one sentence, my research is on data analytics and machine learning for manufacturing systems. So I'm dealing with complex manufacturing systems like steel rolling, steel manufacturing, semiconductor manufacturing, and advanced metrology systems. All these kind of systems generate data, complex data, massive data, and the data of high speed. And using this data wisely, we can perform monitoring, variation modeling, and diagnostic of the system. So I'm a modeler, and I'm achieving this goal through developing new models in data science and developing new computer algorithms. And these models and algorithms are motivated by both data and engineering knowledge. So from data side, we have machine learning, high-dimensional statistics, large-scale optimization, and distributed computing. And from the engineering side, we have domain knowledge and also the structure of the manufacturing system. And also we have the characteristics of the data. So now I'm going to talk about this focus topic, holistic modeling and analysis of multi-stage manufacturing processes with sparse effective inputs and mixed profile outputs. So the keyword here is multi-stage manufacturing process. What is a multi-stage manufacturing process? We can see a typical example in semiconductor manufacturing. So in semiconductor manufacturing, so the chips are fabricated in this way. First, we have a wafer substrate, and onto this wafer substrate, we deposit a thin layer of material, and then it goes through a polish process, and so that this material become flat, and then we apply a thin layer of photoresist material and develop patterns on this photoresist material. And with this pattern, we can selectively etch certain regions of the previous layer. And after another round of deposition and polish, you see, we generate this specific pattern on the second layer. And this process is repeated multiple times in the semiconductor manufacturing process. And finally, we generate this cake-like structure of the circuit. And that's our final product, the computer chips. So from the data side, this process, in every process that generates different kinds of data. For example, after deposition and polish process, we have these film thickness data. And after lithography, we have overlay field. And after etching, we have these profiles of the etched trenches, etc. And at the same time, we can record different potential root causes in different manufacturing steps. They are environmental variables or the information related to the material, etc. Okay. And you see that this process is a typical multi-stage process, and it is characterized by error propagation. Error propagation means that the information from one stage, so the potential root cause from one stage, will not only affect our output from this current stage, but also propagates downstream to other stages. And also you can see that this is a data-rich manufacturing process. In every different stage, you have different types of data. You have curves, you have images, and these curves and images are of different sizes. So how does the industry deal with this type of data? So actually, currently, these different processes are in different departments. So they just perform monitoring, control, and also this virtual metrology inside the different stage. And another kind of approach that they're doing is that they extract the useful features from every stage and then perform modeling. But as you can see, the first approach that generates a scenario of data silos means all these data are analyzed individually, and they do not share the information, and we do not have cannot use their relationship in modeling the quality and for quality improvement. And for the second two steps approach, first extraction and then modeling. So if the feature extraction is wrong, then my final result will be wrong. So what is the objective of this research? I aim at develop a holistic framework for the multi-stage manufacturing process in data-rich environments. And I hope that this approach can achieve three goals. The first one is we can identify the actual root causes that indeed affect the process quality, product quality. And also we can know how these root causes affect the quality measurements. And finally, we want to associate quality measures with several key variation patterns. So the contribution of this work is threefold. First, we propose a general and extendable framework for the data analytic problem for multi-stage manufacturing process. And this general framework can analyze the heterogeneous quality measure and potential root cause simultaneously. And we also developed a solution procedure based on distributed optimization, which is very, very important because this kind of process involves so many data. So before our modeling, so how we deal with this data is dependent on the process and data characteristics. So what are the process and data characteristics? We talked about the error propagation. So the potential root causes may affect the current and the follow-up stages. So we call this the cascading effect. And also, we try to keep a very comprehensive set of potential root causes, and not all of them are troublemakers to my process. So we want to select the actual root causes from them, and we need to consider about the sparsity of actual root causes. And the third thing is the smoothness of the quality measurement. We mentioned that the outputs are mixed profiles, curves, and images. To effectively lower the dimension of the problem, we need to consider about the smoothness property of these curves and images. And the fourth thing is that usually the outputs, quality outputs, are associated with relatively few underlying quality issues. This means for different actual root causes, they may cause similar kinds of quality problems on these outputs. And based on this consideration, we propose a following process model. So there are k stages in total, and for every stage, we have a vector of the potential root causes so they are our measurements. And also for every stage, we have matrix output. That's our quality outputs. And these outputs either represent multiple functional signals or one image. And we assume the linear linear relationship between potential root causes and all these quality outputs. So we develop this linear model, and we consider the cascading effect so that the stage K potential root cause can only affect the stage K, K plus 1, K plus 2, etc. And you see, this is a linear model with scalar inputs and the matrix outputs. And if we collect all of these coefficients together, we have many offset matrices and many effects matrices, and they are the coefficient of our model. Estimating these coefficients is a hard thing to do, but if we obtain these measurements, if we obtain these estimations, we can actually answer all of these three questions we posed before. We can find the actual root causes and find the subspace of all the variation patterns, and we can also know how root cause affect the quality measurements. So to perform this estimation, we formulate a machine learning problem. This problem involves one loss term plus several regularization or penalty terms. And the loss term reflects the magnitude of my prediction error. So that is to say how my potential root cause can be used to, how well my potential root cause can be used to interpret my product quality. And the second and the third term here, they are they are used to represent the smoothness of the response. So because the response quality response are smooth, associated coefficient matrix rows or the entire matrix, they are smooth, depending on whether this stage is associated with multiple curves or a single image, right? So we apply these two smoothness penalization in the second and third term. And for the fourth term here, so we select a potential root cause. We say that not all the potential root causes are actual root causes. If this is not actual root cause, then it will not affect the system at all. So how do we represent this? So we collect all the elements within effect matrix that are associated with this potential root cause Uij, and to try to align them in a vector. And we apply two norm and use this group plus O penalization, and to help us to identify the potential root cause, the actual root causes. And for the first term, we restrict the number of variation patterns of each stage's quality measurements with usage of this nuclear norm penalization. And also that associates the reshaping of my effect matrix here. So in general, if I put everything together, this is my objective function to solve these all the coefficient B's, and that is very, very complex. However, that's a convex formulation. Then how to solve this problem? So we analyze the characteristic of this problem. Well, I do not show the details here. So we apply a parallel ADMM algorithm, consensus algorithm, to solve this problem. And the key step of this algorithm is to update groups of parameters in B and B0 in parallel. And we need to calculate this guy for a different function f's. Specifically, we developed an efficient algorithm for the curve smoother and the image smoother based on discrete cosine transformation. And here is the overview of ADMM consensus algorithm. We just ignore the details in this algorithm, and let me briefly introduce how it works. First, we initialize B and B0 with several replicates. And then in the iteration, we first update different groups of elements in this in each replicate of B and B0 individually, and all these operations can be performed in parallel. And then in a global aggregation step, we aggregate all of the updates for these replicates and calculate their grand average, and to complete this step of iteration. So you can see that if I have parallel computing framework, this algorithm can be achieved effectively. And in the simulation study, we verified this approach using a 4-stage test bed with 20 potential root causes. And you see in different stages that generate different kinds of quality output, either multiple signals of different length or different sizes of images. And we find that this algorithm identify the actual root cause, understand the root cause effect on the profile measurements, and also identify the subspaces of underlying quality issues. So I just skip the details of this simulation study, and here's my summary. So in general, in this work, we propose a holistic modeling and the root cause diagnostic framework for data-rich multi-stage manufacturing process. And so for this framework, we consider multiple root cause in every stage, and the quality measurements of multi-signals or images of different sizes. So the significance, the first one is that this is the first multi-stage manufacturing process analysis method based on distributed optimization. And the second one is that this method is extendable to more types of data by adjusting these loss terms and penalization terms. So highly customizable. And now I'm going to briefly introduce 2 other research topics just for you to get a sense of the flavor of this series of research. And the second one is involved with steel rolling process. And we propose multiple event identification and characterization algorithm by retrospective analysis of the data. What is retrospective analysis? So if you go to you're a data scientist, you go to a factory and say, okay, I can solve your problem. They will give you a data packet of 3 months of production data. And they will ask you this question, hey, buddy, you take a look at my data and what happened in this area, in this 3 months period? And what is the type of variation? And also during what time the variation happened, right? So this is what we mean by retrospective analysis. And the current approach of achieving this is first, we use some quality control methods to identify in which time segments there is something weird happening in this data, and then clustering analysis to see what are the types of faults in these different time segments, right? However, this is not automatic, and the error in detection will lead to wrong classification result. So our goal is in this work is to develop an automatic tool for retrospective analysis. It can perform the event identification and the characterization simultaneously. So here are 3 keywords: what is event, what is identification, what is characterization. So event here means the abnormal variation patterns happen in this, let's say, 3 months period. And identification means we want to find the time intervals when this event occurred. And the characterization means how an event affect the sensor signal, right? So let's see an example. So this is a steel rolling process. And this steel rolling process fabricates rolling bars. And after the fabrication process, this rolling bar here passes this laser gauge. And this laser gauge measures the diameter of this rolling bar along 6 axes. And because we have 6 axes and 6 diameters, so we generate 6 functional profiles from one end to the other end. So for every product, we have 6 functional profiles here. And in total, we have 500 product. So this is the data that we have. And through this events identification and characterization process, we can decompose this one into several types of events. For example, we can see event 1 happens at time from 0 to 100. And event 1 causes this kind of variation pattern to my data. So you see axis 1 is larger at the first half. And for event 2 that happened between 200 and 250, and event 2 is characterized by a tapered end of the rolling bar. So this is the outcome of our algorithm general. How did I achieve this? I actually formulated the dictionary learning algorithm that tackle for the data characteristics and the engineering implication. So here is the optimization problem that I formulated. And here X is my data matrix, right? And this data matrix is decomposed into the multiplication of my event signatures, which are represented using wavelet. Functional data analysis method, and also the strength of the events at different time. And then I used multiple penalizations and to reflect the smoothness of these event signatures and the characteristics of the event sequence. And then I use a blockwise coordinate descent algorithm to solve this problem. And so here's the outcome and the impact. So this approach is validated by a simulation study and the real steel rolling data. And this significantly automate the process of retrospective data analysis, especially when we have multiple functional curves, high dimensional data. And this is a useful and automated tool for quickly understanding the massive processing data. Okay, and finally, I quickly go through this the last example. So this example deal with the tensor data analysis for CT image analysis. So tensor data are like data blocks, either 2D signal array or image sequence, and that frequently appear in many applications. It's high dimensional but content-rich information. And our goal of this study is to uncover the information buried in the tensor object. For example, we can see this is a series of CT image obtained from the aortic valve of human heart. And you can see that there are yellow regions that are the calcium deposition on this vessel. And our goal is to identify their region for reconstruction of the prototype. And our approach is to decompose the data tensor into the summation of 3 parts, background, calcium, and the measurement error, to find what are the region of calcium. And this is our output, right? So corresponding to each frame. So how did we achieve this? Again, we formulated optimization problem where each term tackles different kinds of characteristics of the background and also the calcium deposition and also the measurement error, right? So smooth about the smoothness and the sparsity properties. And then we propose another optimization algorithm based on ADMM allocation to solve this problem. And this is actually a general structural description of tensor objects. And this method is applied not only to this medical problem and also other data analytical problems of tensors. And this also motivates further research of tensor regression, etc. So here's the overview of my research topics. And let me summarize. My research deals with data-driven modeling and analysis inspired by engineering knowledge. And but you see these topics I introduced involving optimization and solve optimization problem, but I also do process monitoring, adaptive sampling, design optimization, etc. So if you're interested in this one, just come to me. And I'm currently actively looking for PhD students. And here are some of the criteria that I have. The most important thing is that you're enthusiastic for data science and motivated for data-related research, and you have a solid background in undergraduate math, especially linear algebra and statistics. And also you have, it's better if you have some coding experience. And finally, I would like to say, if you're studying engineering in your previous experience, this is not a minus, it's a plus, because developing these method and gathering data really need engineering knowledge. And if you are my PhD students, you have the following possible career outcomes. One is that you can become a faculty in the future in IE departments and the national labs, and also you can be a data scientist in industry, like John Deere, Ford, and like Decker, this kind of companies, or also high-tech companies like Apple and Google. Yeah. So thank you very much for your attention.
Time for just one question, quick question. Any questions from anyone? Online students, are there any questions? Okay, so there are no questions. So thank you once again, Professor Mark. And I'm sure some of these students will be in touch with you and talk about potential research opportunities.
Yeah, thank you very much for giving me this opportunity.
You're welcome.
Thanks.
Okay, thanks. Okay, now let me change the setup a little bit, and then we can start talking about today's material. Quick announcements. So by now, you should have some understanding of what the project is, and you could have, you should have actually started working on the project and 3D printing. So I just want to make sure that if there are any questions related to the project, or if there are any questions related to the class, the lesson, I would be happy to answer. Any questions on the material that we have discussed so far? Any questions? Quickly, if you have 3D printed your components from next week onwards, you are welcome to stop by, and I will announce the office hours for Borna along with the checklist. Then you can come and start picking up your parts. But one thing you want to decide is what project you're going to work on, because the microcontroller that you will get will be suitable for the project that you have in mind. For example, if you are going to learn, if you are going to try machine learning, or if you are going to try tic-tac-toe playing robot on the microcontroller, Arduino is not a good platform. Atmel chip, AVR chip is not a good platform, and you should think about using ESP32. If you are going to use some vision-based algorithms, then the platform for you would be ESP32 plus the camera. And there are subtle differences regarding how they are powered, and those will be explained to you when you come to pick up the components. And some students reached out to me saying that in our innovation hub, out of 6 3D printers, 3 3D printers are down. And unfortunately, that is true. So I would strongly recommend, if you have your personal 3D printer, that's the best option. Or if you have purchased a 3D printer and you're done 3D printing, then you can help your friends 3D printing their parts. The other thing is, we have ordered 3 3D printers just for this class. I expect those to be set up early next week. And then if you don't have any background in 3D printing, no background whatsoever, then Borna is going to schedule some sessions wherein you can come, attend the session, see how 3D printing is done, what are the precautions to take, how to make sure that you would get a good 3D printed part all the time, talk about the orientation, filling, support, all that stuff. So I hope that one skill, if you're lacking, you will pick that up in Robotics 1. If you don't want to 3D print, or maybe you are hard pressed for time, if you look at the link, I have added some robots that would potentially work for the project. Couple of those robots you can directly buy from Amazon off the shelf. The cheapest one is for 15 bucks. If you buy the robot, put it together, we will give you the servos. I can give you the servos. The servos that we have will work with those robots. If you want to buy a robot with the servos, just in case if you want to keep the robot with you later for some project, thesis, or just to show off, then you are welcome to buy the robot with the servos. So, and that's not expensive either. But we will provide you with the microcontroller that you need to program the robot. Any questions on the project? Any questions? Okay, one thing I want
yes,
to.
I have a question.
Yeah, tell me.
You had mentioned before that we were gonna, for those that didn't have a particular person to team up with, that you're gonna give that list of people that Borna and we were gonna get teamed up. Is that still the plan?
Unfortunately, I think most of the students have team partners. So if you are in 445, I would encourage you to reach out to the students in class to see if there is anyone who does not have a partner, or you can just choose to do the project on your own, just alone, or you can choose the project from couple of other projects that are individual independent study projects. But that would be my recommendation. Does that sound good?
Yes. All right. Thank you.
Okay. Yes.
We really print our parts at home. You said, do we need to bring those to Borna so we can show it to them so we can get the parts? Or
Yes.
just have a picture of it?
No, you need to bring those parts for a couple of reasons. Because as you know, the quality of 3D print varies depending upon your setting. So before we give you servos, we just want to make sure that the 3D printed parts that you have, and give you some tips based on how to attach the servos. Because I don't know if you know this, servos come with something called as servo horns. Those horns are the attachment from the servo to the part. And depending upon the quality of your 3D printing, you may have to select particular type of horn so that your robot will work. If you have a lot of experience in building robots, servos, RC planes, that's not that's a trivial task. So okay, this is how it is. I'm gonna fit this type of horn. But if you don't have any experience in that area, then I'm sure you'd benefit from some tips from Borna, who actually builds big industrial robots as his hobby. So he would be able to tell you, and you can ask him, hey, my robot seems to be wobbly, or this tolerance is not good. And he will tell you how to make sure, how to remove the backlash, how to add additional components. Maybe he would recommend, if you want to make it look good, nicer, maybe add a sleeve or a bearing, so on. Because please note, one of the projects in your robot is make sure that the robot is not wobbly. And if you want to achieve that, just 3D printed parts won't give you that smoothness. It would be jerky, it would be wobbly. So if you are interested in working on the very first part, I think it's about 15 points. You don't want to work on vision or tic-tac-toe or machine learning, then some tips from Borna will be really good, because then you will have to add either the thrust bearings or the ball bearings, or you need to compensate for the self weight by adding some springs. So it's not straightforward. And you will see, you don't want your robot to break while working. So that's why I said that you need to bring all the parts to Borna. Then Borna can tell you this part is okay, this part is okay. Maybe you have to reprint this part so that your robot would function. Or he may tell you, okay, in this assembly, this is the critical part. And many a time this part breaks. So it might be a good idea to print 2 or 3 parts now, rather than at the last minute when you are trying to get robot working. Does it make sense? You're welcome. Any other questions? Yes.
For the metal bracket robot on that you sent, and then they're all sold out.
There is another link below that link from Amazon.
Oh, okay.
So Sense Smart Robot, unfortunately, is out of stock. It was when I checked it, but I then found out an Amazon replacement, which is on Prime. And if you click on that link, and if that robot is out of stock, there are variants of that robot with the same types of servos. They will work. They will work with our setup. So you can still take that robot, interface that with ESP32 or Arduino that we will provide, and then create an app, and should be able to control the robot what we want to do in the project. Yes.
As long as the servos are the same, then it'll work with our project.
So there are two options. You can buy the robot with the servos, but it's more expensive. So $50. You can buy the robot without the servos, that's fine too. But then once you buy that robot, once you inspect the parts, and once you come to us, we will give you the servos that you will have to return at the end of the class. If you purchase the robot with servos, that robot is yours to keep. Only thing is, perhaps you may have to buy the microcontroller later, and then your robot would be functional and it's yours to keep. Because some of you might want to take that project or that robot and convert that into something else, like a project or a thesis, or that would be a good platform to play with. Yes.
There is another option for developing an iOS app.
You can develop iOS app. That is one of the tasks. So I gave. So basically, unfortunately, if you look at MIT Android Studio, it's a drag and drop, like a blocky thing. So pick, place, and then your app would be developed. For iOS, you need to have first of all, you need to have an Apple laptop or a computer. Then you need to have Swift. Then you need to have the studio and all that stuff. But you can.
So, like there are multiple third-party vendors which are available. They provide the same thing. Where we could develop the iOS apps like drag and drop, like Link and all this stuff.
You can send me the link. I'll try. The reason for that is it may give you app, but then I don't know about the data communication, because that app should have the driver that should talk to the smartphone. It should talk to HT06 or ESP32. That I don't know. I know the link that I have given you It works with H06. It works with ESP32 Bluetooth. It has the built-in drivers. It has the communication protocol. Otherwise, you may have to rewrite your communication protocol. So I don't want to make work unnecessarily complex. You're welcome to do it, but don't be adventurous. Yes.
Whether you 3D print the parts yourself or you go and buy something off the shelf, is the grade gonna be the same? Like
Yes.
I'm grading them differently or?
No, the grade will be the same. Yeah, even though I understand that there are few points for 3D printing, my personal option would be that you pick up as many skills as you can in this course. So I would really like the students to learn how to 3D print. It's a great skill to have. But if you don't want to 3D print, if you just want to buy something off the shelf, that's fine. You won't lose the points. And the reason I wanted to give you this option is because there's a possibility that you may not be able to come to lab, or you may have to self-quarantine or self-isolate. At that time, working in the group is going to be difficult. So you may not have access to 3D printer. So at that time, I want you to have something to work on. That's why I wanted to give you that option. Does that answer your question? Okay. Anything else?
Can we mix and match 3D printed parts with the online available parts? Like suppose consider an end effector. So I got all the links, but I don't want my end effector is wobbly. So could I replace with the online available end effector?
You will have to modify your robot design a little bit, but yes, that is an option. That is an option, but then you will have to. I'm pretty sure if you want to mix and match, you would have to add some components or redesign parts, because then your end effector is going to be heavier than the robot, and robot will fall down, and then you have to balance the weight and all that stuff. But you are welcome to try, but please don't be adventurous. I don't want you to, because if you are not able to get the robot working, or if you are not successful, unfortunately you won't pass the class. Anything else? Okay, fantastic. So let me quickly recap what we were talking about. In the last class, we talked about how to solve this robot arm. This robot arm, we started talking about, this is an R perpendicular to R, parallel to R robot arm. Everyone understood? And what are the rules we use? The first rule is, for frames, the z-axis must pass through the articulation, the rotary joint or reciprocating joint. Then x, so these are the rules. X, n should be perpendicular and intersecting with Zn and Zn minus 1. And the last rule is we need to use right hand coordinate system. So in last class, we worked out on developing the homogeneous transformation matrix that is related to the first joint. Now what I'm going to do is I'm going to write the homogeneous transformation matrix for the second joint, and we are going to start with the rotation matrix. So now what I want to do is 1 R2, and please note, since the axis of articulation is aligned with Z, my rotation matrix is going to remain the same. Cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. But don't forget the important part, which is the projection matrix. The projection matrix, yeah. Yeah, just a second. Zoom quit unexpectedly. Zoom, unfortunately, is giving some problem today. Unfortunately, it all of a sudden it started asking for passcodes. Zoom is quitting. So unfortunately, that's bad. Okay, finally. So what I need to do is I need to have x2, y2, z2, x1, y1, z1, and let's check x2. Can you see x2 is aligned with x1? Are you with me? Y2 is aligned with y1. Are you with me? Z2 is aligned with z1. Are you with me? What that means? This is gonna be 1, 0, 0, 0, 1, 0, 0, 0, 1. Agreed? And the product of these two is going to be my rotation matrix. What would happen to my homogeneous transformation?
Recording in progress.
Yeah, I'm pretty sure there is an issue with Zoom server. I guarantee you there is an issue with Zoom server. Okay, third time is a charm. So now what I'm going to do is I'm going to take a shortcut. So 1H2. 1H2 will have cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Let me fill in the blanks here. 1. And once again, here there are 3 locations. This is the first location, second location, third location. And I'm going to rewrite here what this is. This is position
Recording in progress.
Okay, if Zoom does not work this time, I'm going to start using the board. So this is the position. All right. Okay, let's start. So position of frame 2 with respect to frame 1 along, this is very important, x1
Recording in progress.
Okay. Position of frame 2 with respect to the frame 1 along x1, y1, z1. Now let's start. What do we have? Please note, I'm going to add one distance, which is here, which is A2. I will ask you the very first question. So look at their z-axis. Can you see that those z-axes are aligned? Do you agree with me? Those z-axes are aligned in a sense that they are parallel to each other. Now, my question to you is, first and foremost, can I write 0 over here? Can you hear me now? Okay.
Yeah, you're good.
Okay, awesome. Finally. So today, unfortunately, we have some issues with technology, but nevertheless, we will continue studying. So you have the the first revolute joint that we actually finished. Then you have the second revolute joint, and then you have a third revolute joint, which is over here. And then we have this end effector. And bear with me for a second. Let me set up the z-axis. This is z1. This is z2. Then I have x1 and I have y1 and I have x2 and I have y2. Now the objective here is to find out so 1h2. 1h2 is cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and you have 1 over here. Now I want you to observe that this Z1 and this Z2, they are parallel to each other, but they are in one and same plane. And this plane is not going to change. So what it means is I'm going to write 0 over here. The next thing what I want you to observe is as this joint rotates, this is very important. This is my theta 2. As this joint rotates, this revolute joint, which is frame number 2, is going to rotate with respect to frame number 1. So this is my frame number 1. This is my frame number 2. So frame number 2 is going to rotate. So I want to find out the component or the position in x1, position in y1. Can I, and we looked at this type of problem in last class. Can I write down A2 cosine theta 2 and A2 sine theta 2 as my second homogeneous transformation matrix? It is absolutely important that x1, y1, again, these are the distances, A2 sine theta 2, these are the distances, but these distances must be expressed in the previous frame vector. So it needs to be x1. So please check that you have vector going A2 cosine theta 2 and A2 sine theta 2. When theta 2 is equal to 0, A2 sine theta 2 becomes 0, and this just becomes A2, which is the case in present situation. Everyone understood this? Question? Online question? It's not for. Okay, so this is x1, very important. X1 comes from here. Now what I'm going to do is, and next part is super simple. Last frame, to save my work, I assume this frame to be aligned with the previous frame. So this is x3, y3, z3. And this distance, I'm going to give you as A3. So this distance is A3. Now, what I want you to understand is a super simple example here. First and foremost, what is the rotation transformation corresponding to this joint? So the rotation transformation corresponding to this joint is governed by theta 3. And I'm going to say here 2r3. Again, the rotation is about z. The rotation is about z. So cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1. And never ever forget the projection matrix. Can someone tell me what the projection matrix is going to look like? X3, Y3, Z3, X2, Y2, Z2.
Isn't it the identity matrix?
Okay, yes. This is an identity matrix. So 2, H3, and now you can tell me this is going to be cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, 0, 0, 0, 1. And please note, once again, question?
I don't think they can see that.
Yeah, we can see that.
Okay, so here, please note Z2 and Z3. Z2 and Z3, they are in the same plane. So again, I'm going to write 0 here. Again, please note, this should be Z2, Y2, X2. So X2 is going to become A3 cosine theta 3, A3 sine theta 3, and let's not forget this one. Everyone understood this? Okay. Now, at this point, you can be adventurous and try to perform matrix multiplication by hand, or be lazy like me and go to MATLAB. So that's what I'm going to do. I'm going to open MATLAB. So bear with me just a second, where I actually open MATLAB. Yeah.
Can you put a for up?
What can I do? What do you want me to do?
Put a for up.
Oh, board on top.
Yeah, on top.
Well, if I put board on top, then I think those guys won't be able to see. So why don't I do something like this? Is it good?
Yeah.
And I'm gonna leave this over here so you can take a picture later if you want to. Okay, now let's open our big and bulky MATLAB. And I'm gonna share my MATLAB screen, and then we will work out this problem in MATLAB. And I think I will have just enough time to finish this problem inside MATLAB. So new script. So first line SYMS, because we are going to have symbolic variables, theta 1, theta 2, theta 3. And I'm going to have A1, A2, and A3. A1, A2, and A3. Then H01 is equal to, let me quickly see the homogeneous transformation matrix that we derived. The homogeneous transformation matrix that we derived, and you can correct.
Professor, can you share your screen? We can't see MATLAB.
Okay, yeah. Absolutely. Thanks for pointing that out. I thought it's automatic. Can you see now?
Yes, sir. Thank you.
So it's going to be cosine theta 1. And you can correct me if I'm wrong. Cosine theta 1. Then I have 0. Then I have sine theta 1. Then I have 0, and so on. Then I have sine theta 1. Then I have 0. Then I have minus cosine theta 1. And then I have 0. Again, and so on. Then I have 0. Then I have 1. Then I have 0. And then I have A1. And so on. Then 0, 0, 0, 1. This is my first homogeneous transformation matrix. H12 is equal to, H12 is here, cosine theta 2 minus sine theta 2 0 a2 cosine theta 2 and so on. Sine theta 2 cosine theta 2 0 a2 sine theta 2 0 0 1 0 0 0 0 1 0 and so on. 0 0 0 0 1 0 0 0 1, and I'm just gonna be a little bit lazy because this matrix is going to be same as H2 3. Only difference is instead of cosine theta 2, it's going to be cosine theta 3. Sine theta 3 is going to be A3 cosine theta 3. Sine theta 3 cosine theta 3 A3 sine theta 3. The last step is to find H03. I need to multiply H01 times H12 times H23. Then I'm just going to go ahead here, simplify, because if you were, I'll show you, if you were to just click on this, unfortunately, it will not give you some meaningful expression. So check this out. I'm going to run this code from here to here. And then I'm going to show H03. So if you see, this H03 is a super duper complex and big, and actually it's a fat matrix. Now what I'm going to do is I'm going to simplify say H03, and immediately you will see a nicer expression. So first 3 by 3 matrix is actually going to be your rotation of end effector with respect to the base coordinate frame, and these angles are with respect to your inertial coordinate frame. So basically all these angles, so everything in H03, please understand, everything in H03 is with respect to frame 0. That is super duper important. Everything in this H03 is using the coordinate frame 0. Everyone understood this? Okay, and because this is going to be super important when we are going to find Jacobian and a rotation transformation. So now what I want you to do is, just like last class, I want you to look at these 3 columns, actually the last column, very, very carefully. And what I'm going to do is, whenever you have a forward kinematic solution, I would try to provide some sort of geometric interpretation. So now what I want to show here is, assuming my online students can see me, can my online students see me?
Yeah, I can see you.
Okay, so I want you to look at the board for a second. So this distance is A1. This distance is A1. This angle again it's positive. This is Z naught. This is X naught. And this is Y naught. So what I want you to think about is this is your theta 1. Now for a second, imagine if I want to find out the position of end effector, and this is very important, I want to find out the position of end effector with respect to the inertial frame, which is a zeroth frame. This is where the big zero lies. For a moment, ignore this revolute joint. For a moment, ignore this revolute joint. Do you agree with me that this R, perpendicular R, parallel to R, and I want you to focus on these two R's for a second. This is exactly similar to the problem that we solved earlier, which is like assume that there is no revolute joint and you have the second R, second revolute joint, and third revolute joint. This is like a two pendulum problem. So basically you have a compound pendulum and we derived expression for that guy. You agree with me? What did we derive? We derived, and I'm talking about this with respect to this, we derived something like this. A2 cosine of theta 2 plus then A3 cosine of theta 2 plus theta 3. This is what we derived. And then we derived A2 sine of theta 2 plus A3 sine of theta 2 plus theta 3. Just refer your notes and you will see that is exactly what we derived in last class for two pendulum problems. Do you agree with me? Now what is happening because of this revolute joint? Because of this revolute joint, this pendulum is going to get rotated. Because of this revolute joint, this pendulum is going to get rotated. So what this theta will do is to find out the actual values along, this is very important, and I will try to give you an example. So I want you to look from top. So imagine you are looking from top. What would you see? You would see Z naught coming towards you, X naught and Y naught. Do you agree with me? This is what you are going to see. And what would you see in the top view? In the top view, you are going to see something like this. And this distance, and this may take a little bit of visualization. This distance is going to look like the projection. So basically this is going to look like A2 cosine theta 2 plus A3 cosine of theta 2 plus theta 3. And you are going to have this angle theta 1. So if you look at the X, and I want you to see X, can you see that cosine theta 1 gets multiplied with this entire thing? Can you see that? And if you look down, same thing, except now it gets multiplied by sine. So this is nothing but if you multiply this hypotenuse by cosine theta 1, you get the position in the x direction, x naught direction. And if you take this hypotenuse and multiply that by the sine function, you are going to get this guy. Are you with me so far? And it may be a little difficult to visualize, but just bear with me for a second and I will draw a three-dimensional figure. Now, what happens in the z direction? In z direction, if you look at the projection of this guy, this is going to become A2 sine theta 2 plus A3 sine theta 2 plus theta 3. That is the projection, actually that is the Z direction. And then you are going to add to that A1, which is this vertical distance. And I am out of time, but this I want to show you. Just think about it, like if you have a three-dimensional figure, I would encourage you to think about this, and then it will all make sense. I've spent some time on here discussing this problem, but I'm going to stop here today.